Hello everybody. Welcome to our lecture on learning paradigms. In the last lecture, we talked about a few architectures like LANet, AlexNet, VGGNet. Also, towards the end of the last lecture, we already started looking at residual block. So we said that in principle, a deeper model should achieve no training error than its shallower counterpart. However, we also said that this always doesn't hold true, right? And this led to the development of the residual block. So let us look back a bit at the residual block. Indeed, residual block and the ResNet that is based on the residual block. This is one of the most important CNN architectures. Even today, in many practical applications, the architecture of choice is ResNet. And more importantly, even if we are not using as such ResNet, this particular skip connection that we are seeing here, that is also used in many other architectures that were developed later. So here, what we are seeing, we have our input X, and this is processed by the residual block F1, and we get an output. And what happens here is that the X, this is added back, right? So in a way, so we have not shown here the Z1 in the picture. However, in the equation, we have the Z1, the output Z1 is equal to F1X plus X. So this is one residual block. Let us try to understand what would happen, let's say, if we add one more residual block to this. So we already had the input X. We already said that how this F1 processes this, and we are getting this equation, right? Z1 is equal to F1X plus X. Now we have added another residual block. To this residual block, the input is Z1. And now the output is Z2. And now this output Z2 is F2, which is acting on the Z1 plus the Z1 itself. Similarly, now on the top of this, we can add even more residual blocks. Let's say if we would have added another residual block, Z2 would be the input to that, right? Let's say the block itself is called F3. In that case, we have not written here, however, try to think like how the equation would look like. The Z3 will be F3 Z2 plus Z2, right? And so on. So now let us try to think like why this name residual itself. Equations that we had already seen in the last slide. However, we have written these equations in a slightly different manner, right? So we have written here in the form of F1X the residual block itself is equal to z1 minus x, or f2 z1 is equal to z2 minus z1. So this is what? This is means that this block, each of these blocks, f1 or f2, or if we had added more of them, let's say f3 and so on, they are learning the residual between the desired output and the identity map. So let us try to think a bit about how do we go with the implementation of a residual block. So we will be following the Python conventions here. Not necessarily the implementation is strictly like something that you can just copy to, like a Python code and you can run it. It's more for like just for sake of understanding. So we are talking directly about the forward function, and what we are seeing is that we have the as input x, right? So the first thing that we'll do is that we'll save this x, okay, in another variable here. So this is the identity, right? Why are we calling this identity? Because this is what we will be later using, to add back. Okay, so that's why we have given this name identity. Now the next step will be to actually define my residual block architecture, right? So this is here, we can see these 3 lines. So out is equal to self.conv1. So we have added a convolution layer which is processing this x, and this out itself then is processed with a batch normalization, and then followed by this processed by ReLU, right? So practically what we are seeing here is a convolution layer followed by, for the batch normalization ReLU and all, we will call this as like more as like a post processing layers. Okay, so one convolution layer, that's what we are seeing here. Is that all? Generally no. Generally in a residual block we'll see a number of such convolution layers. So let's see this. So that's what we are seeing now. The out is now again processed using another convolution layer, okay, then again through the batch normalization, and now what we can do is do the step that makes it indeed the residual block. That is, now at this stage we are adding back this identity that we had defined at the top. We are adding back this identity over here. Following this, we are processing again through the ReLU, okay, and now we are returning the output. So this is a sample residual block implementation. Of course, this could be implemented with slightly different variations as well. But this code itself, this enables us to understand the basic principle, like how we store the input as identity, and at later stage after processing the input through multiple convolution layers, convolution and post-processing layers, we are adding back the identity. Now we will move ahead to discuss about next architecture, which is called Densenet. In some way, the Densenet follows similar kind of idea or principle like Resnet. How is that? So it also plays on the connections, more connections. It uses the idea that more connections between the layers may enhance learning. So let us see like how this works in a bit more details. So what happens here is that each layer, this receives input not only from the preceding layer but also from all preceding layer. Thus each layer has direct access to the feature maps generated by all preceding layers. So this principle that we just discussed, okay, that each layer is receiving input from all preceding layers, this will be done in blocks, okay. So this will not be for the entire network, okay. So we will divide the network into several such blocks where each layer receives input from all the preceding layers. So we can call these blocks as dense blocks. And in between these dense blocks, we can have something called transition layer. So one dense block where each layer is receiving input from all the preceding layers, transition layer, another dense block. So what we see here in this figure is a very simple pictorial representation of such dense block. As you can see that given this is the first layer, now this is getting passed to the second one. This third one, we can see it's receiving inputs from the first as well as from the second. The fourth one is receiving input from the first, from the second, and also from the third, right? So the same thing here we have tried to write in a bit more formal equation style. Given the x0, x1, xl minus 1, the concatenation of the feature maps produced in the layers 0, 1, l minus 1, all of these are passed as input to the h. H generally would be a composite function of batch normalization, ReLU, and let's say 3x3 convolution. Of course, this can be done in different ways. Now, what's happening is that if each of these function H produces k feature maps, then the lth layer, how many feature maps it would have? It would have, let's say, some k0 plus k into l minus 1 input feature maps, right? Where k0 is the number of channels, let's say, in the input layer, and then from the each layer the feature maps are adding up. That's getting accounted for in this k into l minus 1 component. So given this information, the natural question that one would ask is that would you choose a large or a small k value? So let's try to reason about this. So think about this, like if you really choose like a large k value, what would happen? As we keep on increasing layers, the number of feature maps will grow large, grow in large number, right? So that's why in general what happens is that Densenet typically uses small k value like k is equal to 12, and this k term, this very specific term, is called growth rate. Now let us talk a bit also about the transition layers. We have already mentioned what is transition layers. They are put between the dense blocks, right? So architecture wise, how they're generally implemented, let us talk it first, and then we'll try to reason out what this is actually doing, right? The transition layers, they generally consist, let's say, of batch normalization, 1x1 convolution layer, followed by, let's say, 2x2 average pooling layer. So think about this 1x1 convolution layer, think about this 2x2 average pooling layer. Why would we put these components there in the transition layer? This will enable us to reason out what this is exactly doing. So there are two functions that it's doing mainly. It's controlling the channel growth, and it's also reducing the feature map size. Think about this. I'm leaving it to you to think about which component in the previous slide that we mentioned is helping in the controlling the channel growth, which component is helping in reducing the feature map size. Now let us change the focus a bit and let us talk a bit about efficient CNNs. We will specifically talk about one particular architecture at this point, and then we will move ahead and stop talking about our architectures for a while. Okay, so the architecture that we are going to talk right now is MobileNet. The MobileNet, this uses a special version of convolution called depthwise separable convolution. So in the last slide, we said that we are going to talk about efficient CNNs, right? The efficiency here, among other things, comes in the terms of number of parameters. So we will discuss more for the next few minutes in terms of number of parameters. So what happens in standard convolution is that the input features are filtered and combined into output features in a single operation. In contrast, the depthwise separable convolution, this divides this process into two distinct functionalities, I will say, one for spatial filtering and the other for channel-wise combination. So how is it done? Let us see a bit pictorially. This will help us to understand. So let's say we have an input which has B channels. So remember, like the CNN feature maps, it could have, let's say, like 32 channels, 64 channels, or some other number, right? So likewise, let us assume that it has B channels. So what we can do is we can divide this into channel 1, channel 2, up to channel B. Now, what we can do on the top of this, we can apply convolution to each of this channel separately and then combine the information. This leads us to get again B channels. Now, is that all? No, right? We would also like to combine information from the different channels, right? So at this point, we have treated the channels separately. We want also a stage where we can actually combine the information from different channels. And this will now be done using 1x1 convolution. The 1x1 convolution will lead us to our output. So let us think a bit. We said that why we are doing this. We are doing this because this is helping us to save on number of parameters, right? So let us try to deduce what is really the reduction factor. Is that worth it at all? So to do this reduction factor, we first need to think about the standard convolution. In standard convolution, let's say we have input channels C in, let's say output channels C out, and let's say we are using kernel size of k cross k. In that case, the number of parameters would be k square C in C out, right? Now, the same thing if we have to calculate for our depthwise separable convolution, what we'll have to do, we'll have to do the calculation in two steps. The first step would be depthwise convolution, where we are applying one k cross k filter per input channel, and this would lead us to number of parameters k square into C in. Now, in the next stage, we'll see pointwise convolution, where we are applying the 1x1 convolution, which are combining the channels, right? And this will lead us to parameters C in into C out. Now, what we have to do is we have to add these two parameters together, and we get total parameters k square C in plus C in C out. This is not still clear maybe whether you are benefiting indeed, right? So let us try to see this through some numbers. So the parameter reduction factor in this case is k square C in C out divided by k square C in plus C in C out. Let us simplify this by assuming that C in is equal to C out is equal to C. So this means this becomes k square C square divided by k square C plus C square, right? Now we can plug in, what we can do is that we can plug in a few numbers here, okay? A few standard numbers, of course. What would be a good reasonable choice for this k? Is not 3 a reasonable choice for k? If you remember, since AlexNet, where there were like use of the 11x11 filters, but after AlexNet, most of the networks, again depends of course, but most of the networks, what we do is use 3x3 filters, right? So let us plug in those values. Let us plug in a value of k is equal to 3 and c is equal to 32, and what we'll see is that this particular parameter reduction factor, the value that we get for this is approximately 7. So this is indeed a nice parameter reduction. If we put different values of c, we'll get different such parameter reduction factor. Since we have talked about the architectures and all, let us also talk very briefly at this point about training in supervised fashion for classification, image classification task. What happens is that the raw scores or the logics that you get from a CNN, let's say, we would like to convert this into a probability distribution, and towards this, the softmax is generally used. The softmax ensures that all the outputs are between 0 and 1 and sums to 1. So we commonly use softmax in the final layer of the classification model, and this helps interpret our model outputs as class probabilities. In most of the cases, the loss that one would use in such tasks is cross entropy loss, which measures the difference between the true labels and the predicted probabilities. So this is, here you can see the equation for the same, and for one hot labels that we use most of the time, this reduces to minus log of probability of the correct class. Now, let us try to reason a bit about that, whether, so we have talked about the architecture, so very briefly mentioned also how we would, let's say, like which loss function we would use. Of course, we can use different choices of loss function as well. However, the question that boils down to at this point of time, that whether this supervised learning that is collecting data, collect more data and train, make some modifications in the architecture. About the architecture, we talked that, okay, like maybe getting the architecture bigger helps at some point. We said that no, let's say it doesn't really help. We face some issues, and we also tried to solve those issues. We saw in the terms of Resnet there. However, the question is that, I mean, is this also, I mean, is this a scalable approach? Is it even possible to collect a significant amount of data for each problem that you would face, or let's say for each domain that you might be working with? The obvious answer is no. There are several situations where it's quite challenging to collect significant data that we would use to train a model from scratch, let's say. And there, The first question that we would ask ourselves is that, is it possible to use the model that has been trained in supervised fashion for some particular task or for some particular domain for other task or for other domain? There we see is that we have several choices. Here we have listed 3 of them. Indeed, there can be other variations as well. So the first choice is that we can use a model which has been trained in supervised fashion. We are trying to use for some other task, some other domain. We could just use as a feature extractor. That is, just use the features that have been extracted from a particular layer without any kind of tuning. Okay. The next choice that we have is actually fine tuning on the target data. That is, further train particular layers of the network. And the third choice is unsupervised domain adaptation. That is, adapt this network with some unlabeled target data. So we'll expand these topics, these choices in the next lecture. Thank you.